So anyway, what I want to do is I want to show you a few projects that have some dimension of randomness in them, and I want to talk about maybe how you might do that in a tool like Grasshopper, and then I want to talk maybe about the theory of that. So I apologize, I don't have these slides well labeled today, but this is a what do I want to call it, like a stadium basically, and you see this facade pattern, and it's pretty much this isn't really like designed. There wasn't someone who went in and actually chose this pattern. There's an idea that's kind of a gradient from this red band up to this white band, and they kind of like you just sort of like dissolve, right? So there's someone just there's a program or there's something that is basically just saying we want more red on this end and less here, and we're going to just keep like removing some until we get that pattern. And so you can do that in something like Rhinoceros. I'll show you how that works. But this idea that randomness can actually, so you think about things just being random and maybe you don't have much control over them, but in fact you can actually say it's like I want to apply a random process to get a specific effect that I want. I don't really care which ones I remove, but I want more removed here and less removed there. Okay, and so that's how we begin to sort of steer randomness and design randomness towards our ends. I'm going to go ahead and open up a script here for you. Yeah, so this is the erosion example, and I'm going to post these online afterwards, but this starts with a surface. So in a lot of these examples, you just have to draw. They'll work with any generic surface that you want to use. So we're going to reference that. Okay, so I'll show you the effect, and then I'll take you back through the script a little bit here. Okay, so this is the surface, and it doesn't look like anything, right? But we do have our friend, the dispatch component here, which is distributing two lists of things. And I have one list of surfaces. Uh-oh, hang on a second here. Something's broken. Supposed to get me two lists here. Something is not working here. Oh, I see. Okay. Yeah, I drew this in the wrong plane. Pardon me. Sorry. This needs to be drawn in the front plane. It relies upon the z-coordinate. Okay. Take two. Okay. So this is the surface, and the dispatch is two lists, and you can think of the dispatch as being like one set of white tiles and one set of red tiles. It's still broken. Okay, hang on a minute. There we go. Okay. In fact, I think I probably need to look at the bounds of this here. Oh yeah, it's super small. Sorry. Okay. Once more. So what I've got is the surface that I have divided up. And I'm looking at the z-coordinate of each of these tiles, and then I'm looking at a random number that I'm just adding a random number to that, and then I'm testing that random number against this component to see whether it's larger than this number or not. And as it tends to go up, it's going to have a greater chance of being, it's going to have a greater chance of failing this test, and so it's going to get subtracted. And so that's how you have more on the bottom and like less at the top. And so that's how this like erosion pattern is going to work. I think in the example, I should have saved the surface I had at home because it was actually pretty well tuned. But you can see how it should start to take away more from the top than from the bottom. It doesn't seem to be doing that right now. But anyway, you can experiment with this on your own. But the idea is that you set up a pattern for yourself so that you know that it's more likely to remove from the top than from the bottom, and we do that by looking at the z coordinate. Okay, that didn't go too well. The next one is this idea that another form of randomness that we see architects using is this idea that you have like a kit of parts, and in this case, this facade there are these 4 kinds of panels that the architects chose. And actually, you can see it better in this example. But there are these like glazed pieces, and then there are these pieces that are solid, and there are like large ones and thin ones. And they basically just came up with a pattern where they just said, we'll just kind of pick them at random, and that's going to create this facade. So some of these are going to be more open, some of these are going to be green, some of these are going to be white, and we'll just keep like building this pattern along the outside of the building. Okay, and that's just an idea that you can do in Grasshopper. There's a component called pick and choose. And so again, we can take a surface, and I'll just go ahead and reference this surface again, and hopefully this is going to work. Maybe it's going to work on a base surface. Right? Hang on. Okay. Yeah. And it's the scale is a little off, but what I've got these forms. I've got circles and rectangles and polygons, and there's a component called pick and choose, or P and C. And what you basically do is that you can feed it. So I have random numbers that are from 0 to 2, and so 0, 1, and 2. And basically what it does is it just picks from a hopper. It just says like, okay, give me 1, 1, 2, 2, 0, 2, 1, 0, and then this is 0, this is 1, and this is 2. And so basically, this is a way that if you've got a series of like parts that you made, and you can reference these as some geometry. They can be parametric geometry. They will basically show up based upon the pattern that you generate from this random number. Okay, and this you can take the pick and choose component, and you can add as many things as you want. So it's unlimited. If you have like 6 things or 4 things or like 2 things or whatever, and basically, I'm just giving it points from that surface, and it just chooses which ones to pull out. So the scale of this is a little wrong. So it's hard to see the effect of it, but it's the same idea as what I showed you in the facade. Let me re-reference that, and maybe it'll show up better for you. There we go. Okay, so triangles, polygons, and squares. And again, this is just the principle of it. This is like not a very good composition, but if you have that component, like the pick and choose component, you can do these kinds of patterns for things. Okay, so that'll be available too. And then the other thing you can do is you can do if you just have 2 things, you can do a dispatch, right? Dispatch takes a list and it pipes the true to this value and false to this value. And here I just have it piping circles and rectangles. And I can just do random numbers between 0 and 1, right? So some of them are 0s, some of them are 1s. 0 is false, 1 is true. And I get the same thing with just 2 things. And I don't need all this pick and choose nonsense. I can just do dispatch. Okay. So those are options. Pick and choose is nice because you can do as many things as you want with it. That thing gets kind of obscenely large. Okay, so with that idea, it might get you into something when you get into a facade like this. This is in the Netherlands. So this is a facade, and this is a much more complicated system. So there's a bunch of these color bands, and they're arranged. There's sort of an order to it. Like they chose colors that were complementary to each other. There's kind of figured ground relationships in this system, but the actual way that they put them together is pretty much random. So someone designed the system, but then ultimately it was basically created in a random manner to kind of create these effects. Like they weren't exactly sure what they were going to get. And it would be very hard to do this on your own, right? To go through and say, okay, this is a red one, that's a blue one, that's a green one, that's a blue one, that's a blue one, that's a blue one, that's a green one. Like you would be very hard for you to make it look random. But for a computer, it's like trivial, right? A computer is not going to have to think about patterns for things, okay? And so you can actually get these kind of nice layered effects. But you have to know enough about like composition to actually choose the right colors and to choose the right proportions of this thing. And then you can begin to apply these kinds of principles, these kinds of parametric principles to it. It's only effective in the presence of both of those things. But they weren't maybe aware that it was going to sort of create this more blue area, this more kind of like red area. That's actually just something that kind of happened in the process. Okay. This is another one. This is at NYU that just recently went up. Does anybody know what this is? This is a anti-suicide curtain. So this is people had problems with this library, I guess, because it was a big open area, and so they created this screen so that you can still see in and out of it, but it's going to prevent people from going off of the ends of the library. So these are all just wooden pieces. I know, right? Pretty dire. But they have these people that just put these tiles on these wooden strings, and it's just a random pattern now.
They did that on middle schools too. They just put bars.
This is better than bars, probably, right? Yeah. So, but anyway, just an interesting thing to say. Like, they have these pieces that they cut that have different lengths of them, and they just put them in a basket, and then the people who like strung them up just pick them up like randomly. So, this is a thing that you could do on the computer as well, and I think it's kind of a nice like field effect. But anyway, there's just an example of that, and that could also be a pick and choose. Like you would create a bunch of little like Tetris pieces and then assemble them onto your grid. This is a building that's proposed, I believe, in Abu Dhabi, but this is idea of a facade that's made up of, again, kind of a random configuration of transparent, opaque, and matte and reflective tiles. And what they do though is that they do have a proportion of these, so they know that it's going to be random, but they say that like 50% of the building's facade will be transparent, okay, and 50% will be opaque. But then they just kind of so there's probably some poor soul who like has an office here who just didn't get any like transparent tiles, right? I'm sure they probably check that.
Do they distribute people randomly too?
Probably not. No. But it's maybe it's democratic. I don't know. This is the Yamaha headquarters in Ginza. And again, this is a facade, and there's kind of like the first one I showed you with sort of like the erosion, where there are these kind of bands of like gold and bronze and kind of glass, just clear glass, and they're kind of shuffled and also kind of eroded from each other, so that towards the top of the building the tiles become more of this kind of glass. And this one, yeah.
I thought maybe like one side was opaque, the other side was transparent.
No, they're actually there are these fins, and on a lot of them, you can see there's two transparents and then two opaques and then one on the other. So yeah. Anyway, the night reversal I think is quite nice. Like in this one, you can actually begin to see some of the interior kind of spaces of it. It's actually like a curtain wall system. It's on the outside of the building, so it's not just like pure just like wallpaper. I think it actually has a nice, and there are various like transparencies and various kinds of opacities. That motif gets repeated on the inside of the building in this kind of concert, because it's Yamaha, right? So they're going to have a Yamaha piano, in there, and so there's a system as well of these kind of acoustic tiles, and they're also quasi-random. You can see they sort of start to erode as they go up towards the ceiling. Okay, so just some examples here. This is another building. I believe this is in China. I got to get my credits on here, but there's this composition, right? That there's the building, and there are the voids and the entry, and then the rest of it is kind of a canvas. And there are these openings. There are very large, kind of openings, and there are these like smaller things. It's all like a grid. It's like your first year kind of grid, right? You have your pieces of trace paper that you can kind of move around. And they kind of let the computer kind of pack this thing. And actually, they're probably modular so that they have space around them. You notice that they don't actually run into each other. They're not actually like touching each other to create shapes. And they did actually leave open like this corner. So there's some design going on here. But really, they did kind of leave a lot of this to like chance operations. And the effect of it, is kind of interesting to kind of like dissolve that form and to kind of play with. I mean, this is kind of a double high space, but when you get inside the space, it also starts to happen, and even into the openings of the ceiling. As those columns like dissolve into the openings, and then even into the treatment of the columns, they're actually doing this kind of like random. Like this one actually dissolves towards the center, and then it becomes more opaque towards the bottom and the top again. And again, it's just this kind of effect that they wanted to create, and so they employ these kind of random processes, and that's what a space would look like on the inside of the. I have no idea. There's nothing in this room. I don't know what they do with it, but it's interesting that those become kind of floor to ceiling walls or windows, but then you have like a window that's like shin height, So anyway, maybe that's kind of of interest. This is a building in China, and this is an example. So the last ones I showed you were just kind of examples of random distribution. Let's call it that, right? You have a series of like openings or closures or transparencies or opacities or colors, and you're randomly distributing them. Or you're distributing them with some kind of design randomness, which we'll talk about in a bit. This is an example of what I want to call jitter, okay? And a jitter is when you have something that's regular, but you put like a little bit of randomness into it. So this is a grid, but it's like perturbed, right? Like they've been moved slightly in the x coordinate, okay, right? Like if this is a grid, that's your x, and let's assume, that's your x, yeah, and that's your y. I guess they've actually been, yeah, so they have common kind of datum lines, and they're not moving like up or down into each other, right? The y is not, or the z is not being disturbed, but there's a little bit of slant to them, like as they merge into each other. Like this vertex is being moved just slightly off of that grid. And that creates, it's an interesting effect, right? Because you have the regularity, but then you have the kind of like irregularity, like the instability of that form. So I'm going to show you an example of jitter in Grasshopper. Oh, there we go. Okay. Oh, no. Oh, no. Data access component. What? Okay. Let's try that again. I might not have. Okay. Let's kill these here. Sometimes we have bugs. Ah, okay. So, we started with... Hang on a minute here. Okay. So it starts with a regular kind of grid, right? We like divide our surface up, and it's a nice regular everyday kind of grid. Then what we do is we decompose the points. Remember we talked about this with logic last week? We can get access to the coordinates of the points, the x-coordinate, the y-coordinate, and the z-coordinate. The x and the y get fed to a new point. They're fine. Like we don't touch them in this case. Oh, actually, this is another example. I want to show you this jitter, this xy surface. Let me do this one first. Sorry. Got ahead of myself here. Okay. We'll do the xy first, and then I'll do z. That's the z example. Stand by here. Okay. Okay. We'll hide this too. Same startup though, right? We have the surface that we decompose, and then I take the x and the y, and I feed them through some random things, and I say basically I'm gonna add or subtract 5 to your x coordinate, and then put you back together again as a surface. So that's the kind of jitter. And then what you end up with. So the green ones are the new locations of the points, and the red ones are the old locations of the points. Okay, and that actually gives you going to give you a new surface here. Let me see if I can get this to come up as a. Yeah, so that actually begins to fragment that surface. from what it used to be. And then we can actually play with that. Let me turn off these other points here. Getting kind of confusing there. And then we actually can fragment it in the Y as well. And so that used to be a grid, but we tweaked it. And the less you like jitter it, so when we get it, so it's just like fractionally, jittered. It becomes like a little bit more stable as a form, but it's still just slightly off kilter. Right?
Either add 0.9 or subtract 0.9 instead of add 8.9.
Oh, either add or?
Yeah, not like.
You can do kind of a dispatch thing where you like pipe the list through and you do a random number between 0 and 1, right? It's 0 or 1, and then one list gets 9 and one list gets -9.
So you have to do a dispatch.
Yeah, you gotta do it. You gotta do it like, you have to do it that way. Basically, use a random to pick between two numbers. I know it's a little bit kind of counterintuitive, right? It's kind of like flipping a coin, though. Right? Heads it's 9, tails it's -9.
What do you do if you did a true false situation? Would you did one -1 with 0.5 or 1 0 with 0.5 round up?
You can set it to just do integers, and so it'll only do 1 or 0. Yeah, so you don't have to worry about rounding at all. Yeah, good question. If you want me to talk about it with you later, I can do an example of that. But yeah, I mean, randomness can be used to do like a coin flip or like a roll of a die, right? Do 1 through 6. Any kind of system that you want to like experiment with, you can have random start to help make decisions for you. But here I'm just using it as a random number generator, to kind of jitter these things. But that's one example of a jitter. The other thing that you can do that you guys probably might find useful in your designs is when you can jitter, you take a regular surface and you jitter it in the z-axis just to create a rougher surface. And so here what I've done is I just took the x and the y's are the same, but I actually jittered the z, and that creates a disturbed surface. And again, if I adjust the density of these, so there's less jitter, right? It's more flat. It's like a piece of paper or something, but then as I do it, it becomes more like fractal, more sort of like topographic. Okay. We're going to talk a little bit more about like why we would do something like this, but I think some of you guys have been kind of interested in these kinds of processes before. It's hard to see. The points are not exact. The points create a surface which is an approximation, and so they don't actually always touch those points. But that's what that is. That is a surface. That's a grid that the x, y's are the same, but the z's are shifted. Okay. So that's jitter. You can see a couple other examples of that. But the effect of it is kind of interesting because it's like it plays off of the order. It's like we have a system, we have a regularity, we have a module, but we do like a little extra something to it. We add a little bit of salt to it, a little bit of spice to it to make it a little bit more interesting for us. And we're not. It's arbitrary. It's not as ordered. I mean, we still have some control over it, right? I can play with those sliders to really take it out of alignment or just barely take it out of alignment. But I'm not in control of each individual little minute adjustment in that. And that's kind of what's interesting about using the computer in this kind of scenario, right? We're interested in the end result, but we're not completely in control of that process. We're in control of it up to the point where we can select the inputs. And we can choose what the output is, what the final output is, but we don't have every vertex I'm not making a decision about. Right, like you would in a model, right, or in CAD. It's automated. Does anybody know what this is? This is the Coca-Cola Pavilion at the Olympics in London. This is the Coca-Cola Beatbox. And it's a space that you can, the building's like a musical instrument, and you can like play it by like running through it and hitting things and whatever. This is an example of kind of modeling in a random way. So there's essentially just like a pile of these modules that were just kind of assembled, quasi-randomly, and they kind of like intersect each other. And then what they did was they just kind of eroded a space in there, and that's what they actually created the sort of like pavilion out of. But we're not. So the pavilion sits like inside of this like random kind of assortment and they just like took out pieces that got in the way, basically. But they just kind of played a game with this, where they just kind of, in the computer, threw these things around and let them fly around on all three axes. And then, of course, the bottom ones, it's like a Coca-Cola can or like a Coca-Cola logo. It's got white on the bottom and like red on the top. So as like an additive modeling, process, you can even engage like randomness in architecture. And somebody's actually paying for this stuff, somewhere. So anyway, I mean, we can argue whether we like it aesthetically or not. But I just want to say, just as a kind of idea, this is something that somebody attempted. But as I always say in architecture, when I teach you some of this stuff, like, and I think Nick reminded me of this, Nick Bradford. Yeah, man. Hey, use this for good and not for evil. All right. So this is an example of maybe evil. Like this is kind of a crazy building. This is this big eroded cube. And look at this thing. I mean, forget the fact that it's orange for a minute here. But there's just this kind of random, like kind of assortment. Like, I don't really know what it has to do with the offices on the inside. As you guys mentioned, like, are we paying attention to like who's occupying it or like how they're occupying it? It's kind of a one-liner. It's kind of a gimmick, like for the sake of the gimmick. Okay, right? It's just a conventional building wrapped in like IKEA, those little like storage containers, that you can get at IKEA. Totally insulting the architect here, but you don't want to do like this kind of thing. It's not just like wallpaper. You want to think about, like, I don't think that there's really much going on in terms of like compositional rules, or that they're really thinking about the like sizes of the circles, or like how they like relate to each other, how they relate to the street, how they relate to the interior occupants or things like that. It's just a big orange block. I mean, I think when you look at some of the examples of some of these things that I'm showing you, though, at least they do, you may disagree with them, but at least I think they have a logic behind them. Maybe not this one so much. Like I think about this one, and I like it as a composition, right? I could see this hanging in a museum or something, just as a piece. But the cheese block. What, the last one?
Yeah.
I'm going to like put the links up for these, and you guys can find. I think it's in France. The Death Star. Yeah, cheese blocks. They don't sell cheese there. I know that. Like, it's actually something else. But isn't that? There's like a nice little river there, and they have this. Anyway, so this begins a dialogue about like how should we or how might we think about randomness in design. Like, I've shown you some examples of this, and I've kind of like try to explain how you might do that in a Grasshopper. But now that I've kind of given you the tools and I've shown you it, you have to ask yourself, like, where does this like factor into the kinds of things that I might want to make, or how are architects actually thinking about this? And so I want to sort of talk about that in a little bit. We think about things like this is just noise, right? This is like pure randomness. I mean, this is but it's not really that interesting to us. Like, if we have just a kind of pure randomness, no choice, no like order whatsoever, that's not really design. Okay, at least I don't really think so. So just having randomness and as an agent isn't really enough, as I've tried to say. It's not really interesting to us. When you think about something like a Jackson Pollock like painting, right? And you'd say like, okay, this is like fairly random still. But it's not quite, because Pollock chose the paint. Pollock had an idea for the like composition in mind, like as he's like throwing the paint on the canvas. There are some things that he's not in control of, right? Such as the physics, maybe the exact viscosity, the like air resistance at the moment, that he throws it off the brush. But he can see what's happening in the composition as it like takes shape. He can see how the color is starting to like build. He can try to like undo things that he sees that he's not liking. So like he's a partner with like randomness, but he's not being like taken over by randomness. Randomness is not like it's not like a gimmick in his work, right? It actually adds a bit of like complexity to what he's like doing with us, okay? And that's where it becomes interesting for us, because computers can be these like randomness machines. They can be these partners in this design process, where sometimes we don't want to quite be so much in control of like everything, right? We want to be surprised by what we see. How often does that really happen? when you're tooling away in CAD or whatever, you're like, wow, where did that come from? It's like, no, I drew like that, you know? I mean, really, maybe in modeling, you know, maybe things like that, but there is a real desire there to be surprised, and we like that, like when that happens, and when that happens in the computer, we get like feedback. Okay, and so that's what, and this is mid-century, right? Like they are experimenting with like chance and with like loss of control and in the creative process. And now we have the computer, and of course we're like way behind, but here's where we are. So order can be, you know, it can be useful, it can be aesthetic, but it can also be kind of like boring. It can be kind of regular, right? If everything is like banal, like that's not very exciting. And chaos can be boring too. Like if everything is noise, like where do we come in, or where does the design, right? So I think we aim for might be complexity is an idea that we might be striving for. Complexity is a very complex term, and a lot of people might argue with me about my definition of it. But think about this like gaseous nebula. How many times do you hear that? Think about this nebula, and there are some rules involved in it. There's like hydrogen gas, and there are all kinds of particles, and there's all kinds of dust, and there's like fusion happening. So there are some rules involved in it, but the complexity of all those things interacting with each other is actually what causes us to see like what this is, and it's almost like beyond our like comprehension. There's order, but there's so many things going on, even though they're ordered, that it just verges on chaos, or it verges on something that we can't like probably like control. And that is, I think, what we might be seeing in these kinds of things, and what we might be trying to capture when we allow the computer to like take some of that from us, is we want to try to like inject some complexity into like what we're trying to do. And complexity is very hard for us, you know, hard for us to manage. But we have algorithms now, and we can even kind of simulate, like in a way, the kind of nebula by creating simpler. I mean, again, the rules that are affecting that are very simple, and the computer can simulate them for us, and then we can arrive at something that's very close to that, right? And so that's one of the things that's interesting about computational design and procedural design, is that we're sort of experimenting with these processes in order to sort of capture that. But again, going back to mid-century, you know, think about John Cage. He's a composer and an artist, and he had a series called Chance Operations, and he was looking at devices like the I Ching and like dice and things, and basically saying that like, I'm going to create a musical piece, or I'm going to create a poem or a composition just by like throwing dice and just by putting things together, and it's that sort of overturning that idea that, you know, there were only certain things that could be music, or there are only certain things that could be beautiful, and just saying like, as the artist, like my role is to be in control of this process, but maybe I'm not in control of that like product, you know. And then Gene Arp, you know, again was making visual compositions on the same rules, like basically throwing things at a canvas or rolling dice again in order to randomly create these compositions. The pieces though are still in control of the artist, like the dice or the I Ching or the rules or the words that are selected, or the shapes in the canvas or whatever, but the processes were left open, or like left open to chance, and they were really trying to experiment with this and say like, is this art? Like, is this an artist? If an artist like does this, okay? And so these are things that we're still kind of confronting. Is like, where's sort of like the autonomy? Where's the design in this process? This is Tim Knowles, and Knowles does these things. So these are quasi-random. He does things like, he has a car, and in the back of it is a pen on a spring, on a pendulum, and he drives around the Autobahn, and he like swerves his car, and the spring motion like creates a drawing of it, right? So, you know, he's in control of the car, but he's not in control of the pen, and the physics of it, the spring motion, the like pendulum, is actually creating that drawing. And then here's the thing, which I find just like stunningly beautiful. He ties a brush with sumi ink on it on the end of a fir tree, and just lets it blow in the wind, you know, on this canvas here. And so again, he's kind of set the tone. It's like white paper, black ink, and he set the location or whatever, but he's kind of letting it, you know, construct the drawing, right? It's his drawing. but it's not something he's in. It might, I mean, like 20 of these might be stunningly bad, you know, from our standpoint. One of them might be beautiful, but does that even matter? Like, isn't this like what's really kind of beautiful about this process? So that's something to consider also, and that's something that we want to think about when we're working with the computer. So we talk about, you know, randomness can be complex. So we had pure randomness, which was noise. And I sort of steered us away from that. And the alternative here, though, is I think you have randomness that has rules and constraints. So you talk about things like serialism, which is a form of musical composition that has these very strict rules to it. And it's like you can only create music in a certain way when you're creating it in a serial system, and it's you know, quasi-random. But anything that's made in that system is like serialism. It's of that system, and one can only play within that system. And then you have this other thing where you have a system that has play in it. So I set it up, and it has rules and constraints. Like it can't really go any further than the length of this branch or than the length of the pen that's attached to it, right? That's a constraint in the system. But the randomness comes in the way the wind, you know, blows, which I have no control over. You know, the flexibility of the tree, which again I have no control over. Maybe there's fluids in the tree that control it, and I'm left with whatever kind of comes out of that system. In the computer, we can do this by saying, you know, you can create rules. So we have like the coin flip. We can say if we flip one way, it's -9. If we flip another way, it's +9. That creates kind of a system that we're doing. Or the other thing is, what I'm getting to the end of the lecture here, is automatic machines. So we can create a system that actually begins to follow its own rules a bit, that we have even less control over. So it's even more than a coin flip. Okay, we have machines that actually make more decisions, and they make multiple decisions for things. We have like automated agents. We'll talk about that in a second. We get this idea about designing processes. This is I think it's a mouse in a cage, and it's attached to a drawing apparatus and a wheel. And as the mouse moves around the cage, this thing keeps going around, and it's actually drawing. It's actually creating a drawing based on the balance of the cage and where the mouse is in it. So again, this is this kind of thing where like I'm not in control of the mouse. This thing is kind of running on its own on a motor, but it's constructing this like drawing. We can't really do these kinds of things in Grasshopper because we don't really have the capacity. It's a very linear process. There's no feedback in the system. We've talked about this in several weeks here. This is a feedback, you know, system. Like the mouse does something, the system does something, and the thing spins around again, and then the thing repeats itself over and over and over again, right? We don't have that kind of capability. We can do things like the spirograph, right? Where we have like a fixed apparatus that we can control the kind of like parameters over. We can change the angle of the pen, or we can change the number of times we go around it, but like it's pretty much not. There's no like feedback in that system, and it's not really like it's difficult to make it respond to things. The other thing we can do though is procedural generative design, and this is what I study, and a lot of things that I make are involved in, and what we might be doing in advanced comp methods this semester. This is a line from LeWitt, and it's this idea that he was an artist this past century. You guys studied LeWitt in first year? No? Okay. A previous class it had. LeWitt thought of this idea that the idea was actually what the art was. Is the idea becomes a machine that makes the art. So instead of the artist making the art, maybe the artist makes the idea, and then some other agent produces the art. That's a really interesting idea. So this is LeWitt. And these are some examples of some of his work. He has a piece at the Beckler. What LeWitt did was he created instructions for art that then other draftsmen or painters could then make. And they were dependent upon the variables of the gallery or other variables that he like determined. And he was very particular about the instructions. He's like, you can only use like this color paint. You can only use like this pencil. It has to be in this kind of space, right? But the space in the gallery that you would put the art in would actually change it, because it actually would be made in that gallery. Okay, you don't like transport a LeWitt, you like make it on site. So if you go to the Whitney, there's a LeWitt in there, and it was drawn like in the Whitney. If you go to the Beckler, it was painted like at the Beckler because of the space. Okay, but what he like sold were the instructions. Like that'll be $1 million, you know, right, for that instruction, and then some draftsmen go and make this piece. So he was a programmer in a way, right? I mean, predating all that stuff. And it was his way of saying like this idea of avoiding subjectivity, so like kind of taking oneself a little bit out of the piece, and also this idea of saying that like I'm designing these as a series. Like I have a piece of art, and it can be in 10 different galleries at the same time, and it's still the art, and it's a little bit different because of each space. The plan designs the work. Okay, so this is one example of one of his pieces, and these beautiful like simple pieces, right? 12-inch grid covering the wall, and each grid 1 arc from the corner. That's the instruction, right? Like 2 lines. And the direction of the arcs and the placement are determined by the draftsman. So the draftsman is a person, and draftsman goes in and draws an arc. And the arcs, there can be 4 different arcs, right? You can rotate the arc around 4 different ways. It's a white arc on a black field, and just by accumulating them over time, you get these like compositions, okay? So it's like a choose 4 if you were doing this. I mean, I hate to like put this into Grasshopper, but you have 4 different like arcs, or 1 arc that's rotated 4 different ways. Put them on a grid, right? You can run this thing, a million different times and do different things, but I think they're all kind of beautiful, right? Because of the rules that he set up, they're kind of beautiful. Wall drawing, one person, the first draftsman draws with a black marker, and then another draftsman, and you draw like a regular line, and then the next one comes in with another marker and draws a line without touching it, and then one comes in, and it's kind of like a game of telephone or something where the line, just through the kind of accumulation and the kind of like, play in the person's hand starts to become different. It's just as beautiful because of the colors that are chosen, because of the scale of it, because of the character of the line. It just becomes this beautiful kind of piece of art, right? But it's in this like repetition, and it's in this like the randomness that the individual introduces into each line and into the first line that makes it a really interesting process. Okay. Wall drawing. So this is a piece that you actually connect lines from all of the vertices in a room together with blue construction chalk. And this will be different in whatever space that this is executed in. And it makes you more aware of the kind of architectural space. And again, it's a process, right? You look at a room, you wouldn't exactly be sure like what it's going to be until you actually construct it. And I would say that about all of these, which is cool. So this idea is like, the serial artist does not attempt to produce an object, a beautiful object, but really just records the results. Like, so it's like I have a process for these kinds of things, but I'm not trying to make it beautiful. I'm just trying to make what the instructions like say that I'm supposed to make. And that's actually what's important. I'm just cataloging the results. He has this background that I have here is this thing that's like all the different variations of a planar cube by subtracting and adding lines. He just went through every single line in the series, and this is the work, is the whole thing. It's every single permutation of this cube. This is a catalog of this form. Okay. You might consider this valuing process over product. And we talk about this, and we don't have time to unpack this quite a bit, but we talk about mass customization, or we talk about being able to make things on demand, and it's this idea that you could make each one of these things like separately from this process. And actually, I forgot this. Well, there's a set of teapots by Alessi that are by if I can browse this, that are by Greg Lynn. You guys know Greg Lynn? He's an architect. Greg Lynn. And Greg Lynn did a series of teapots, and they're based on a script. So there's some geometry that sort of gets like manipulated in the computer, and there's a series of 99 of these, and they cost like thousands of dollars each. But basically, there's a series of these teapots, and they're cast in titanium, and they're all based on a parametric script. And each one is slightly different. And some of them, I think, like don't even work as teapots. But to him, the important thing is not the individual teapot, whether or not it's beautiful or not, but it's actually the series of the teapots. It's the 99 teapots that he created that's actually the work. Okay, it's a little weird, right? But to him, it's that idea of the sequence and of that process, not whether or not you got the right teapot or the most beautiful teapot. It's hard to see, but they kind of fold together in like a petal. They're each slightly kind of bulbous and slightly different. But we're beginning to think about this thing. It's like if you have machines that can just fabricate patterns, or that can make every single kind of permutation of something. Maybe that's like a direction we're headed in, where we're just thinking about the kind of series and not thinking about making one perfect, like, beautiful thing, but maybe we're thinking about all the possibilities of that thing. And that's kind of philosophical, but I want to end with LeWitt with this idea, though, that simple rules can be beautiful. I mean, look at this. This one is called arcs from the midpoints of two sides of the wall. So he takes like two radii very far away, and he draws like arcs between them. And they're the same distance, and as they become to move together, they become to like oscillate with each other, they become to make like these more arrays. So you don't have to have all this like crazy algorithms and computation and like weird stuff. It's just repetition and geometry and order, can be really beautiful. It can be really like engaging. So you don't like this kind of thing, right? There's a lot of stuff that we see. But there's something about this, which is definitely procedural and definitely could be computational, that I think we don't want to disregard. You can make blobs like all day, but I think there are still some things that we can explore with like planar forms and with geometry that might be interesting to us. These are some artists that you might look into. This is Marius Watts. And these are just points that are traveling along sine waves that just like intersect each other. And he's choosing the colors and things like that. But it's actually a very simple process. And sometimes the points are being laid down very slowly or very quickly, and that's what actually creates the differences in the spacing of the patterns. And I mean, Watts has a program that just can make these things like all day, right? But these are like procedural art. And here's another one. These are vertical lines that are then that just kind of turn, and again the spacing changes in them and the color changes in them, and these are arcs. I mean, these are circles that then begin to become disturbed with sine waves, and they overlap in two different color bands. And there's just this kind of exploration of simple rules. This is John Maeda. He's probably one of the like pioneers of computational procedural art. These are simply like lines that come out from a center point to the ends of this piece. But he's doing different things, like he's stopping them at certain points, and then he's like shifting the color a bit, and he's doing that in multiple intervals as they like overlap each other to kind of create this effect. These are lozenge kind of shapes that are irregular, and he just keeps overlapping them and overlapping them and overlapping them, and they're kind of jittered a bit, and then until they create this kind of field. So just very simple, like procedural kinds of processes. So like I encourage you guys to explore, simple geometries and repetition, and just slight bits of like all of these are incorporating randomness and a little bit of a loss of control. They're not quite the disciplined. I mean, the randomness in LeWitt comes from like where you choose to make the radii and how good your draftsman is, right? Or like what choices the draftsman makes. But I like the kind of, there's a little bit more play in these than there are in those. They're both very, very beautiful, but these feel like sort of like overdone, or maybe that they're not in as much control, in my opinion. But another Maeda, which I like, I think is quite beautiful, just vertical lines intersecting each other, and there's a bit of jitter in those as they kind of slide past each other. Another Maeda. So this is process ink, and just lines of circles overlapping each other. Jared Tarbell, he does things with more granular computational stuff. So he works with pixels as they shift. So instead of like circles and lines, he actually uses pixel operations. And he creates these kind of sandstone kind of patterns from each other. And these are different kinds of tonal fields of these. And these are jittered. There's like a pixel, and every time it moves, it makes a copy of itself. And it goes up, it goes down, it goes left, it goes right, and then he just kind of starts and stops them. So these are not very well jittered. These have jittered quite a bit, and as the pixels overlap each other, right, the alphas like create different kind of field effects, and that's what he gets. There's another one, and this kind of creates almost kind of like like a texture, like almost like a textile. These are very strongly vertically jittered, and they're in rows with each other. Okay. So to do these kinds of things, you're going to need a bigger boat. You're going to get into a different tool, and that tool, one that I like quite a bit is called processing, and this is one that I encourage you guys, if you're still interested in computational design, and you're interested in some of the things that I showed you, it's not possible really in Grasshopper because of the things I talked about. There's not a lot of feedback in the system. You don't have looping in the way that you want. You need actually to get into a real programming language, and processing is a tool that makes it as easy as it can probably be. So Grasshopper is graphical. It works in Rhino. Processing is a standalone application. It's based on Java. You've probably heard of Java. You guys all had to do the wireless network upgrade. It runs on Java. Processing is actually writing code, but it's very simple code, and it's code that talks to lines and colors and circles and things like that. It's a language for talking to shapes, okay? And it's open source, which means all the code's openly available. It's free. It's for artists and architects and designers and people who want to do like interactive things. You can download it for free. I'll post a link to it. But it's being used by professionals, students, artists, researchers. I mean, there are actually scientists that are using it for visualization. The New York Times uses it to do its like infographics. It's being used in printmaking, fabrication. There's architects that use it. It's a very widely used tool. SciArc is using it in studios. And it allows you a lot more flexibility than I think we've been used to in Grasshopper. One of the other things you can do with it, too, is that processing can actually talk to Arduinos, which are these little breakout boards here. And they can be used to drive things that are mechanical. So you can have code that can talk to, like, a model, right? So you can have a model that responds to, forces or responds to proximity or actually like adjust itself. So if you learn, you guys actually already know a lot about coding because of the work we've done in Grasshopper. Because of the work we've done in Grasshopper. You can transfer that to processing and really get into a lot of interesting things. This is a project called the Mechanical Mirror, and Rosen has a series of these. This is a webcam in this, and it's looking at this woman. And there's a series of dowels, and they rotate. And because of the way the light is in the gallery, it's very specific. You actually construct a grayscale image of what the mirror sees in that camera. So it's a mirror of what the camera is seeing, and it's just like the rotation of these dowels. Now we've talked about this before, right? In our Grasshopper, it's like you have a parameter, which is a grayscale image, right? There's a series of values, and those values are just mapped to the rotation of the dowel. You guys know about rotation now. You can talk to that. So you guys, almost could like program this if you knew the language. You know the ideas of this. You know how to break down the problem of it. You just don't have the right tools yet, okay? This is actually like, when you get down to it with the tools we have now, kind of a simple problem. Now, getting, I don't know how many dozen, actuators or whatever they've got in this thing, to do that is another thing. But the logic of it, the process of it, actually, you're very close to having. This is another one that's a series of disks that have patterns on them, and they also rotate to create a mirror image. There's a camera in the middle of this image, and these just rotate. And so the computer is controlling the rotation of those images. Because the whole series of these things, they're beautiful, and they're all mechanical. This is some data visualization. So like taking sources of data, we talk about this a lot in terms of like sustainability, in terms of environmental analysis, demographic information, GIS, taking it and actually literally plotting out the graphs over time and turning them on a spindle. And this is a 3D printed form. But processing can produce 3D form, and that can be sent to a 3D printer. And so these are actually models of this data as it changes over time. So the data is an artifact, actually. There's other examples of that. This is a changing like sound wave like over time, and this is cut plexiglass on a laser cutter. And processing analyzes the sound, constructs the curves, and then sends it off to the 3D printer or to the laser cutter. Another example of that. So you can begin to work with other media using. So right now in Grasshopper, we're kind of stuck with like we have kind of numbers, we have 3D form, we have 2D form. Processing can talk to other machines. It can talk to other software. It can look at other media like video. It can look at sound. It can talk to Wii controllers. It can talk to Microsoft Kinect. It interfaces with lots of things, and that can be used to actually drive like formal processes. Okay. This is a sound wave converted to the radii of some circles, and they're laser cut. This is a couple saying "I do," and it's like a bracelet made out of that. So again, converting one media to another. Okay. And then we get into something else that you can do with this that you can't do with Grasshopper, which is you get autonomous like agents or like swarms. And you guys may have seen architecture that looks like this. So we talked about saw LeWitt and the beauty of simple rules, and we talked about the things like jitter, where it's just a simple operation of moving something one pixel or moving it back a pixel or up and down. But what if you had a lot of things that follow simple rules, but they respond to each other and they respond to their environment, like a swarm of ants or like a flock of birds, okay? And there are experiments going on with this in architecture. You get this property of like surprise again, this property of like emergence. I'm going to give these things a mission. They're going to want to find an attractor or find a light source, and they're going to leave a trail behind them. And over time, that trail is going to tell me something. It's going to tell me about the most efficient route to something, or it's going to tell me, it's going to be a self-reinforcing path. But I don't know what's going to happen until I let these little critters like run around. And that's something that we're experimenting with in computational design. This idea is like are there orders that we don't know exist or that we can be surprised by? These are Brandenburg vehicles. And this is one kind of like autonomous agent. And okay, so these things in the computer are little pixels, but the model of them, the concept, is that they're little toy like robots that have wheels and little sensors in them. And the Brandenburg vehicle, so there's little eyes here, and if an eye sees a light source, it turns the wheel. And if it doesn't, then it doesn't turn. And what happens is that if you configure one like this, it's going to turn towards this like light source. If you configure the wheels like this, it's going to turn away from that light source. So that's a very basic kind of robot. And believe it or not, so I need to plug in my computer. If you put a swarm of these things in a system with different attractors, light sources, they create patterns. And I'm going to show you what this looks like in a second. And I'll show you a use of this, something I did. It's not architectural, but something I did for a design. So Brandenburg vehicles look like, so this is a light source, and I can move it around. And this is a Brandenburg vehicle that's wired, so that one of the wires is wired to the opposite, so the eye is wired to the opposite tire. And so it's going to keep turning like towards the light. And see, it can't find the light. And it still has a little bit of motion left, and it's going to speed up and move towards that light source. Okay, and then until it hits it and bounces off. This is the other kind of Brandenburg vehicle that's wired so that the eye is wired to the same tire, and that's going to turn away from my light. It's going to run away from it as much as possible. I can chase it away. Okay, so you can experiment with these. There's different kinds. Anyway, so that's a Brandenburg vehicle. Then if you have a swarm of Brandenburg vehicles, they begin to lay down paths and trails. And so there's an image here, and that's the light source, is the values of those pixels. And what happens is, you can see this happening, is that as the vehicles move, they actually begin to brighten up the image. And when the image becomes brighter, that actually begins to affect their path, right? They're actually affecting their own environment and making themselves follow those paths. And eventually they're going to stabilize along the paths that they create.
Are they moving the light sources too?
They're moving, this particular version has these little like obstacles, and that's to kind of introduce some like randomness into it. They just kind of push them out of the way until they move again. But no, the image, the light, and the trails are all that's actually affecting their travel. And I'll give you this code as well. And again, this is something that we're experimenting in fields like complexity, theory, and in you know, like network analysis and stuff. And because you don't know, every time you run this, you don't know what's going to actually emerge from the system. But it's going to have some kind of order because there are these rigorous, you know, rules that the system follows. Anyway, it's just something, just food for thought. But I want to show you an example. We'll come back to this in a minute and see what happens. But I want to show you an example of a project that I did. This is one of my other this is one of my colleagues from MIT, and he wrote a book called Conceptions of Design in a Culture of Simulation. So he was looking at the ways that architecture firms use simulations from a cultural standpoint. I won't go into it, but that's his face. So he has this press photo that he always uses, and I make fun of him about it because he looks like a criminal, you know, in this thing. It's almost like a mugshot. And I was thinking about these, like, when I think about simulations now, I think about fluid dynamics, or I think about cosmological simulations. I think about, like, false color images. And I was like, what if I could find a way to, like, simulate something about his head and then make it like a false color? And so what I actually did was I modified some of that Bratenberg code to run over an image of his head. And so it would trace the, like, light that's found in his face. So it traces over his ear. It traces over the bridge of his nose. It traces through his beard, okay. And then what I did was I took the grayscale and I made some like false color filters and processing, and I ended up with the image, you know, that you see below, and that was the image that we published for that lecture. So that was an example of a little design that I did that used these ideas, and you know, like, I couldn't draw that. There's no way. Like, you wouldn't draw something like that, and it's going to be slightly different every time I run it, and I just find that really, really interesting, and I think it had something to do with what he was talking about. I'll just show you briefly just a demo of what that thing looks like. If I can find the image of it somewhere. Oh, where did it go? Hang on a second. Is it going to another window? I don't have another window. What's happening to it? All right. Well, maybe I'll post it. Okay. Anyway, it's kind of like that Bratenberg example that I showed you. Sorry about that. You can see this one's starting to stabilize a bit more. Yeah, we'll go back. Okay. So. What's that? It's based on ideas like ants leave pheromone trails, and then they follow the same trails. It's similar to that idea, exactly. But I mean, obviously, ants are much more complicated. This is just a few lines of code, you know. But the similarities are interesting, you know. So we started the semester with this question about what is computational methods. The very first slide of the class, and I may have confused that a bit today, but I think that you know, at this point, I hope you guys have a sense of where these kinds of ideas about, you know, like repetition and variation and logic can impact your designs and impact your design thinking, and you know, some sense of where this might be headed, like some of the things that architects have been doing with it, some of the things where it might be impacting what you're doing in studio, and hopefully have inspired you a little bit to try some of this yourself after the class. You know, all this is building towards, you know, where the profession's headed in terms of information management. But, you know, this is, you know, Revit, and Revit's like parametric, and Revit is, you know, definitely like data-based. But there's so much more to it and so much more potential to these ideas than just the low-hanging fruit of like BIM, okay? What you've done in this class is going to help you understand BIM a little bit better, because it's been abstracted away from some of the complexities of the like building process and of the software itself. But on the other hand, it's also going to take you, you know, in a direction, you know, maybe towards some of the weirder, more interesting things that are happening on the fringes of computational design. So I don't, you know, hopefully there's been some value to that with you. You know, we looked at these projects that have been done in Grasshopper. By now, you know, when we first showed this to you, you probably had no idea what was going on with this. Now you have some sense of what you saw here in this pattern. what's actually going on with like the repetition of these patterns, and actually how it can be kind of difficult to work with when you get to something that's this complicated, right? That's actually where I think programming can kind of step in and can optimize these kinds of things and can abstract them for us and make them actually easier to work with. I think Grasshopper like has kind of a ceiling. At a certain point, you kind of like outgrow it, or the problem outgrows it. And I think it's very useful because it's very visual, and I think it allows us to make things in Rhino and get things out of it really nicely. But I think for like some of the more complex problems that we're going to be encountering, it finds its limits. Okay, and so as we look at computational architecture, it's been happening in the world at least for the last decade. We're really seeing the use of computation in solving forms and in resolving problems, making things more efficient, and trying out new ideas in forms. These ideas that we're talking about are really going to become everyday and going to become commonplace. And that's why we think we need classes like computational. Why we need classes like computational methods. So hopefully it's been a valuable semester for you. There's two things due. One is the final project, and two is a class survey that I'm going to post online. You guys do know that this is part of my research into computational pedagogy, and so I would appreciate your feedback on the course, on my survey, as well as the class evaluations. Okay, but thank you guys for a great semester, and I'll see you around.